Hello and welcome to this video on determining whether a given transformation is linear. Now we have seen this in prior videos of mine. I put up a video in the past where we had to determine whether a given transformation was linear, but those were transformations between two vector spaces that were Euclidean spaces, right, from like R2 to R3, R4 to R5, etc. Now we're looking at more general transformations, right, from one vector space V, say, to another vector space, maybe called W. And they don't have to be necessarily the Euclidean vector spaces. They could be, but I'm going much more general now. So I'm going to start off this video by defining what does it mean for a transformation to be considered a linear transformation. Then I'm going to go over several examples where we're given a transformation from one vector space to another vector space, and it's going to be assumed that it's under standard operations, right? The standard definitions for vector addition and scalar multiplication under those vector spaces. And that's the last part of the video. All these examples where I'm trying to show whether or not a given transformation between two vector spaces is a linear transformation. Okay. So on the first page here, right, it's got linear. What does it mean for a transformation to be a linear transformation? So suppose we let V and W be vector spaces, right, with given definitions of vector addition and scalar multiplication. The transformation, T from V into W is a linear transformation if for all vectors in V, say vector U and vector V belonging to vector space V, and for any scalar R, right? Now this R could belong to some field, right? But typically we're going to say that that field is the real numbers. All right. So the following two properties have to hold for every pair of vectors from the domain, right, V, and any scalar R. And these might look familiar, right? Again, when I talked about linear transformations between Euclidean vector spaces, Rn and Rm, these two same properties have to hold this additivity property and homogeneity property. In other words, linear transformations preserve vector addition, which is this additivity property, and preserve scalar multiplication, which is this homogeneity property. Pardon me. So the additivity property is if I were to take the sum of the two vectors u and v. Now you got to be careful sometimes, right? With Euclidean spaces, I was saying we're working under standard operations, and both the domain and the codomain were Rn, Rm. So vector addition and scalar multiplication were defined the same way in both those spaces. So here, when I'm talking addition inside the parentheses here, this addition is addition in V. Right, this is vector addition the way it is defined in V, right, in the domain. So I apply addition first and then perform the transformation, right? Then apply the transformation. And if this transformation T is a linear transformation, this should give me an equivalent result to if I were to apply the transformation to vector u first and then to vector v and then added them. But this addition over here is in the codomain, right? Because when I take the transformation, when I apply a transformation to a vector, the result is a vector in the codomain, right? So this is a vector in W, this T of u, and so is this T of V. This is also a vector in W. So when I perform addition on this side, this is addition in W, addition in the codomain. however addition is defined for that vector space. Okay, and the same thing goes for the homogeneity property, right? When I'm talking scalar multiplication. On the left side here, I have a t of r times u, right? A scalar multiple of u. This is where I perform the scalar multiple of u first. I do scalar multiplication first. And this vector u is a vector from the domain, a vector from V. So the way I would perform scalar multiplication in here is the way scalar multiplication is defined in V, right? So this is scalar multiplication in V that's being performed here in the parentheses. All right. And then after doing the scalar multiplication, I apply the transformation to it. And then the final result, right, will be some vector from W, right, the codomain. Well, if this is a linear transformation, this should be equivalent to the scalar r times t of u, almost like you're pulling the scalar out, if you want to think of it that way. Now here, when I'm doing scalar multiplication here, right, r times t of u, t of u, this is a vector in W, right? This is a vector in the codomain. So I'm doing a scalar multiple of a vector in W. So that scalar multiplication I need to perform is the way scalar multiplication is defined in vector space W. Right, so this side I'm doing scalar multiplication the way it is defined in W. Right, in the codomain. So I hope that's clear. Right, just be careful. Sometimes, your vector spaces, they may be like totally different looking vector spaces, so the way vector addition is defined in V may not be exactly the same way vector addition is defined in W. And the same thing goes for scalar multiplication in V and in W. Just pay attention as to, what are my vectors I'm performing operations on? Are they from V, or are the vectors I'm performing operations on from W? Are they from the domain, or are they from the codomain? Right. So just pay attention to that. All right, so in the rest of the video, I've got just several examples where I'm given a transformation from one vector space into another, and I'm given a rule for that transformation. And then I'm asked, simply, is it a linear transformation or not? Is it linear or non-linear? And I'm just going to be verifying that, are these two true? Now, both of these have to be true in order for it to be linear. If one of these fails, it's not linear. All right. Okay, so let's get into it. My first example, and again, these directions are the same for every example here. Just determine whether the given transformation is linear. All right, so this time, instead of going from Euclidean space to Euclidean space, I have a transformation from this this vector space of this set of all 2 by 2 matrices with real entries. My inputs are going to be 2 by 2 matrices, and my output, all the outputs are going to be from P3. All right, remember this P3, this was the set of all polynomials of degree 3 or less. All right. And the, vector addition and scalar multiplication in this vector space, the domain, is the way you normally add. I'm going to do the standard operation, standard matrix addition and standard scalar multiplication of matrices. Right? And then vector addition and scalar multiplication in P3, vector addition is just when, adding polynomials together, right? Combining like terms. That's your standard vector, polynomial addition. And scalar multiplication, if I multiply a polynomial by a scalar, the standard way to do that would be just to distribute that scalar, right? So that's your standard vector addition and standard scalar multiplication for P3. So just keep that in mind, right? The way vector addition and scalar multiplication are defined in these vector spaces are different, right? Okay. And the rule for this transformation is this. T of, again, my input here, my vector is a 2 by 2 matrix with real entries. So A, B, C, and D here are real numbers. And the output is, see, a polynomial that's degree 3 or less, because if A were 0, you'd have a degree 2. If A and B were both 0, you'd have a degree 1, and so on. Right? So my output is a polynomial of degree 3 or less, which just has these entries as coefficients of the polynomial, ax cubed plus bx squared plus cx plus d. Okay, so as with the definition of linear transformation, right? Remember those two properties, the additivity and homogeneity properties, had to hold for any pair of vectors from the domain and any scalar. So I'm going to start off by saying let's just take any pair of vectors from the domain, and I'm going to call them u and v, like back in the definition. You can call them something else if you want. But I'll take U be the 2 by 2, a 2 by 2 matrix, right? Something from the domain, and it just represents a general vector, a general 2 by 2 matrix. And again, I'm just going to call these entries here U1, U2, U3, and U4, so I know they're from vector U. And I'm also going to let another generic vector, some general vector representation of any vector from R2 by 2, call it V, with entries V1, V2, V3, and V4. Right, so these represent any pair of vectors, any vectors at all from the domain set, right, from the domain vector space. And I'm going to let lowercase r belong to the field of scalars. Now again, I didn't mention any particular field. That would be my set of scalars up here, and I've mentioned this before in other videos if you've been watching. If a particular field of scalars is not mentioned, just assume it's going to be the field of the real numbers, right? So this is my set of scalars here. All right, so R here is this is any representing any scalar, right? And these two U and V are representing any vectors from the domain from that R 2 by 2. All right, so first I'm going to try this, see if the additivity property holds, right? Does this transformation preserve vector addition? All right, so first, additivity. So I'm going to ask this question. I'm actually going to write it out here for this first example. Is the value of t at u plus v equivalent to the value of t at u plus the value of t at v? All right. Now again, this is a question. I do not know the answer to this. I do not know that this is true, so you cannot start off by writing that these are equal and then moving things to other sides and whatnot. You can't write this. You don't know this, right? So what I will do is work with each side individually and see if they actually give me the same result. So let's start with let's say the left side here. I'll just say left side or LS in the future. So what is the value of t at u plus v? All right, so here I'm performing addition in that R 2 by 2 first, right? I'm adding the vectors u and v, which are these two matrices, and it's the standard addition. I mentioned it's standard matrix addition. So I'll have t of, and if I were to add these two matrices, the usual way you add matrices, we'd get this 2 by 2 matrix. u1 plus v1 for the first row, first column component, then u2 plus v2 for the first row, second column component, u3 plus v3 for the second row, first column entry, and u4 plus v4 for the second row, second column entry, right? So that's u plus v doing addition in R2 by 2, right? Doing addition from that vector space. All right, and then I apply the rule to this matrix, right? And then I apply transformation t to this matrix. And what I'm getting here is, again, all of these entries just become the coefficients of some polynomial of degree 3 or less. So I have u1 plus v1 times x cubed plus, I'm just replacing a with u1 plus v1, b with u2 plus v2, c with u3 plus v3, and d with u4 plus v4 in this, right? So plus, and then u2 plus v2, right? That's all replacing b there, so it's in parentheses times x squared plus, and then u3 plus plus v3. All that is replacing c times x, and plus, and if you want to put parentheses around this, you can. It's replacing something. u4 plus v4 replacing the d. Okay, wonderful. All right, and then if you'd like, all right, you can see here how, if I wanted to get rid of all the parentheses, I can distribute the x cubes here. These are all representing like, some real numbers here, so you can distribute multiplication over addition. So this is u1 x cubed plus v1 x cubed plus, doing the same thing here with the x squared, right? u2 x squared plus v2 x squared. Doing the same thing with the x on this set of parentheses. This is plus u3x plus v3x. And then, again, there's really no need for these parentheses here on the last part because it's like you're distributing 1. So I just got u4 plus v4. All right, so that was the left side. All right, totally simplified, no parentheses and junk, right? So let's take a look at the right side of this. Again, do not say that these are equal. Right, we're trying to show that they're equal. All right, so looking at the right side, that's what is t of u plus t of v. All right, so in this case, right, I apply the transformation to matrix u, vector u, right, so to this, and that would give me the following, t of u, right, and here's the rule again up here, and here's vector u, right, with this 2 by 2 matrix with u1 through u4. If I apply t to this matrix, that means u1 replaces a, u2 replaces b, u3 replaces c, u4 replaces d. So t of u is u1 x cubed plus u2 x squared plus u3x plus u4. All right, that's t of u in the parentheses I've got here. And then this is being added to t of v. Now t of v, same thing. I'm applying the same rule here to vector v. So v1 would be the a, v2 would be b, v3 would be c, and v4 would be d. All right. So t of v, again, in this set of parentheses, I'm replacing it. I like to put parentheses around what I replace. Would be v1 times x cubed plus v2 times x squared plus v3 times x plus v4. And really, there's no need for the parentheses here because, there's nothing to distribute other than the number 1. So just imagine this is without the parentheses right now because, again, they're not necessary. And look at these. Look at the result of the left side performing t of u plus v, and the result of the right side taking t of u plus t of v. Are they the same? Do they have the same expression in the end? Are they the same result? Well, look, u1 x cubed, u1 x cubed, u2 x squared, u2 x squared, u3x, u3x, u4, u4. Got those 4 terms in common. Plus v1x cubed plus v1x cubed plus v2x squared plus v2x squared plus v3x plus v3x plus v4 plus v4. Every term is accounted for on this, and every term is accounted for on this. They all have the same terms. They are the same expression. They are equal. So what we're seeing here is that t of u plus v is indeed equal to t of u plus t of v for any vectors u and v, right? These could be these u1s through u4s and v1s through v4s, right? They could be anything, any number I wished. Alright, so the answer to that question in the beginning was, yes. Yes, it is. The additivity property holds true for this particular transformation. Okay, so that's part one, right? That does not say that the transformation is linear, right? Because it may have this property be true, but then the homogeneity property isn't true, right? So you have to show both are true to show a transformation is linear, right? So we have the additivity. All right, so now the next question is about the homogeneity property, right? That's preserving scalar multiplication. Right, so I'll write the question again. So again, here's the transformation. I'm letting u and v be any vectors from the domain, r be any scalar, any real number. All right, and then part two. And again, I'll ask that question: is the value of t at ru, r times u, the scalar multiple of u, is that equivalent to pulling that scalar out, r times t of u? Right, does it satisfy the homogeneity property? Again, I'm asking this question. I do not know this. You do not know this is true. So you can't start off by saying that they are equal and then moving things to sides and all that, adding and subtracting from both sides. There is no equation here. Right? I'm trying to show that it's true. I can't start off with it then. I can't start off assuming that it's true. Alright, so as I did with the last one, let's take a look at the expression on the left side. I'll call this ls. So what does t of ru look like? Right, so what is the image of r times u? Alright, so this is telling me I do scalar multiplication first. And this is scalar multiplication in R2 by 2, in this vector space in the domain. Remember, U is a matrix, and this is doing scalar multiplication of a matrix, right? And again, I said it was standard definition of scalar multiplication here. So I'm just multiplying each entry by R. So this is T of the 2 by 2 matrix RU1, RU2, RU3, RU4. And then I actually take this now, this RU, and apply the rule of T to it. So this is A, this is B, this is C, this is D now. And I'm getting RU1 times x cubed plus RU2 times x squared plus RU3 times x, then plus RU4. Wonderful. And that's as simple as that would get. Right? There's no parentheses, nothing to distribute or anything like that. Okay, and then I'm going to do the same on the other side. Right? Again, I don't know that these are true yet. I don't know this is an equation yet. We'll see if they're equal. So let's look at what the expression on the right side is. So I have r times t of u. All right, so this is a scalar r multiplied by, and then this time I'm taking t of u. I'm applying this rule to vector u, which I did in the additivity property lines as well. That would give me, now again, when you replace something, I'm replacing t of u with its output, right, with the image of u. That was put parentheses around it, right? So that'd be u1 x cubed plus u2 x squared plus u3 x plus u4. And now I perform scalar multiplication, but this is scalar multiplication in P3, not scalar multiplication in R2 by 2. Scalar multiplication in P3 is simply, when you multiply a polynomial by a scalar, the standard operation is to distribute. So I distribute that r. We have ru1 x cubed plus ru2 x squared plus ru3 x plus ru4. And then look at this expression compared to that one, right? The t of ru versus the r times t of u. ru1 x cubed, ru1 x cubed, plus ru2 x squared, plus ru2 x squared, plus ru3x, plus ru3x, plus ru4, plus ru4, and every term down here is accounted for, every term up there is accounted for. They are indeed equal. So yes, the answer to the question is yes, and therefore that homogeneity property holds. Therefore, t of r times u is equal to r times t of u, for any vector u, for any vector from the domain, right, from R2 by 2 there, and any scalar, right, R belonging to the real numbers. All right, so check on that, right? The homogeneity property holds, the additivity property holds. So we can finally at the end here say, therefore, T, right, that transformation called T here, is a linear transformation. Wonderful. Okay, great. And this is what you got to go through. Now again, if one of them fails, it's not. And I'd also say if one of them fails, you could also probably think of a nice counter example, right? Just show me one example as to why it fails, right? Give me one specific vector from the domain and one specific scalar, where you're using actual numbers and showing that this isn't always true. Or if you're showing the additivity property is false, find two specific vectors such that that additivity statement isn't true as well. All right, so the first example I had there was a linear transformation. Here's another one. All right, so now there's a Euclidean space here, R3, but notice that the first vector space, the domain, is not a Euclidean space. So this time transformation is called S, and it's from P2 into R3. So my inputs are going to be, again, this is the polynomials of degree 2 or less. They all look like this, right? Ax squared plus bx plus c, right? So I'm taking a polynomial of degree 2 or less, plugging it into S, and then the output is a vector with 3 components, right? With real number components, R3. So here's the rule. S takes this input of ax squared plus bx plus c, polynomial of degree 2 or less, and the output is a vector from R3, with 3 real numbered components, where the components are a plus 1, b plus c, and c, right? Where this a, b, and c are coming from here, right? They're coming from the input. All right, so as before, right, when you're trying to show, I'm trying to show that this additivity and homogeneity property hold for this particular transformation. So I need to make a statement about, start off with just, those should be, the additivity property, right, should hold for any pair of vectors from the domain. And the homogeneity property should hold for any vector from the domain and any scalar. So I want some representations of any vectors, a pair of vectors from the domain and a scalar. So again I'll call them u and v. All right, so say vector u here is again a polynomial from P2. Again, just to know that they're from u, I'll just call it u1 x squared plus u2x plus u3, right, where the u1, u2, and u3 are like the a, b, and c. And vector v here, again, I'll use v1 x squared plus v2 x plus v3, right, where v1, v2, and v3 are again like the a, b, and c. They're just the coefficients of the polynomial. These belong to P2. Right? And just some representative of a scalar, right? Again, I'll just use again the lowercase r represents any scalar. So these are any vectors from P2, and this is any scalar. All right, so just as before, first question, check that additivity property. So number 1, I'll write it again this time, is the value of S, right, the transformation is called S this time, at u plus v, is that equivalent to S at u plus S at v? Question. Right? I don't know this, so again, you can't start with this. You can't just set them equal automatically and then work with that equation. You have to show that it is a true equation. Right? Okay, so again here with the left side, I'll just start with that left expression, see what I get from that. So what is S of u plus v? All right, so remember, u and v are polynomials. Right? They're degree 2 or less polynomials, these guys here. So when I'm performing addition here, it's just the adding of polynomials. Right? So the addition inside here is the addition from P2. So when doing that, I'd have S of, remember when you add two polynomials, you combine like terms. So the u1x squared plus v1x squared would make, u1 plus v1 x squared when I combine like terms, right? And then u2x plus v2x, so the x term is, got a coefficient of u2 plus v2. And then the constants, you're adding, again, you're adding u and v, u3 plus v3 would be the constant term, so plus u3 plus v3. All right, so now my input, the u1 plus v1 is like the A now, the u2 plus v2 is like that B, the u3 plus v3 is like that C up there. And then I take the sum of u and v and apply transformation S to this. And again, this is going to give me an output that's in R3. Right, so a vector with 3 components. Let's make a little brackets here. The first component was, a plus 1. So the coefficient of x squared plus 1. So that's the u1 plus v1 plus 1. All right. The second component of the output was b plus c, right? That's the coefficient of x plus the constant. So the coefficient of x plus the constant, so u2 plus v2 plus, and then u3 plus v3. And if you want to put parentheses around these things, that's fine, but really there's no need for them here because there's nothing to distribute. And the final component of the output was c, that was just a constant term, so u3 plus v3. Okay, so that's what I'm getting with the expression on the left. Now, let's see what happens when I look at the expression on the right of this, right? So the right side. So what is S of u plus S at v, and see, hopefully I get the same thing back. If not, if they're not exactly the same looking output, then I should be able to find a counterexample to this, a specific pair of vectors where this isn't true. And I'll show you after this is done. Alright, so S of u. Now remember, u is this u1x squared u2 plus u2x plus u3. So the u1, u2, and u3 are the a, b, and c here. So S of u is this, again, the output is a vector from R3. First component is going to be, u1 plus 1. Second component is going to be u2 plus u3, right? The b and the c, u2 plus u3. And the third component is just c, the constant u3. Okay. This here, what I just wrote, is S of u. And I'm adding to this S of v. Right. Now v, right, was this polynomial. Again, I'm just basically, instead of u1, u2, u3, it's v1, v2, v3. Right. So this is v1 plus 1 for the first component, v2 plus v3 for the second, and then v3 for the third. And now when I'm performing addition, right, now we're adding vectors, adding matrices pretty much. So we're doing vector addition from R3, not from P2, right? Remember this addition here, this addition was adding polynomials. This addition is adding vectors, different definitions. But just make sure you know what space you're in. Right? Am I in the domain or am I in the codomain? Here I have vectors from the codomain, so I'm doing the codomain's definition of addition. All right, so in adding these, the first, again, standard definition here, I just add them component-wise. So u1 plus u1 plus 1 plus v1 plus 1. That'd be u1 plus v1 plus 2, wouldn't it? Right, because you have the 1 plus 1 as well. And then you have u2 plus u3 plus v2 plus v3, and then u3 plus v3 for the third component. Sorry about the tininess of the subscripts there. Now look, I mean, the second component is the same as the second component here, right? u2 plus u3 plus v2 plus v3, same stuff. The third components are the same, u3 plus v3. It's these first components that might be different, and well, definitely will be different. Right? These first components are not the same, so these are not going to be equal. And I could actually stop here and say they're not equal. So the answer to this question I asked up here, does that additivity property hold? Right, the answer is, is no. So then this transformation S is not a linear transformation. But I'd also like to show with a counter example to this statement. I'd like to show that this is false by showing it's false just once. By finding just some, so here is a counter example. That's where I find two specific vectors u and v. Again, I could kind of stop here and say they're not going to be the same, but let's look at a counter example. So I'm going to take two specific vectors from P2, two specific polynomials. So say u is, again, this is from the domain, this is from P2, so a polynomial of degree 2 or less. So about u is x squared minus 3x plus 1. And say v is just 4x minus 5, right? Whatever, just polynomial, these are from P2, right? And these are specific vectors from P2. Then let's take a look. What's S of u plus v? That would be S of, now here I'm doing the addition of polynomials first. If I were to add these polynomials, I'd have x squared plus x minus 4. And then I apply S to this. All right, remember the rule for S. Rule for S is up here. So when I apply S to x squared plus x minus 4, the A is 1, B is 1, and C is negative 4. So I'd have 1 plus 1, or 2 up in the first component. B plus C would be 1 plus negative 4. There'd be negative 3 for the second component. And then C, the constant, negative 4 for the third component. So the result of S at the sum of these two specific vectors from P2, the resulting vector is 2, negative 3, negative 4, and this is from R3, right? The outputs should be from the codomain. And now let's look at S of u plus S of v. All right, now S of u is just for this polynomial, right? This polynomial, x squared minus 3x plus 1. So A is 1, B is negative 3, C is 1. So the result, if I apply that rule to it, it would be 1 plus 1 for the first component, 2. Then B plus C, right? Negative 3 plus 1, negative 2 for the second component, and then C for the third component. So there's S of u, 2, negative 2, 1 from R3. Then I'm adding to this, S of v. Now A is 0, so it'd be 0 plus 1, or 1 for the first component, and then B plus C, 4 plus negative 5 would be negative 1 for the second component, and then C, negative 5 for the third component. And again, now when I do addition, now it's not adding polynomials, it's the addition in R3, it's adding these vectors. And when I add these, standard definition too, standard addition, just add the components. 2 plus 1 is 3, negative 2 plus negative 1 is negative 3, 1 plus negative 5 is negative 4. And you can see very clearly now that these are not the same. Right, these are not equal because of that first component, right? As we set up here, the first components won't be the same. The second and third components will be the same. You see negative 3, negative 3, negative 4, negative 4. But the first components, 2 and 3, are not the same, right? So these are not equal. All right, so we have just shown through that one counter example and also through the statement before, right? We have just shown that s of u plus v is not equal to s of u plus s of v. Right? Okay. So that tells me that s is not a linear transformation. I'll just say not linear. Okay, great. So I'll keep going. Just got a couple more examples here. Hopefully this is making some sense. All right, so here's one. You calculus people out there, right? Remember, this is the first derivative of some expression. Now we're doing polynomials, derivatives of polynomials here. Now you may recall from calculus 1. You may recall that they, maybe they, I don't know, whatever text you were reading, but remember the differential operator, the first derivative was a linear operator, they called it. I'm sure that was mentioned at some point. Whether you remember it or not is fine. You're going to see that the first derivative operation here is a linear operation. This will be a linear transformation. We'll see that here. All right, so we have this transformation called Q from the set of all polynomials of degree 2 or less to the set of polynomials degree 1 or less. All right, so my input looks like this: ax squared plus bx plus c. And then my output is the first derivative of my input, right? The same input here over there, the derivative of the input. Now I can go through again just the calculus rules here. The derivative of polynomials are easy, right? This is just use the power rule here. This would be 2ax plus b, and then plus 0, right? The derivative of a constant was nothing. So I'm just going to leave it like this, right? So my input is some polynomial degree 2 or less, ax squared plus bx plus c. Output is 2ax plus b, right? This is a polynomial of degree 1 or less, right? Some coefficient times x plus some constant term. All right. So just as before, I'm gonna take just two general vectors from P2 from my domain. So u equals this time instead of u1, instead of all the subscripts, I'm going to say ax squared plus bx plus c for u, right, where a, b, and c can be any numbers. And a vector v that is dx squared plus, now I don't typically like to use the lowercase e for a representative of a number because e is a number, 2.71828 and so on. So instead of, I'll skip over e and say fx plus g. Right. Where again a, b, c, d, f, g, these are just numbers, right? And these belong to P2, right? These are polynomials of degree 2 or less. And let r here again, but be any real number, is our scalar. All right. So same as the last two examples, right? Question 1. Now this time I'm not going to write the question. All right, I'll just put 1. We're looking at the additivity property, right? So first I'll evaluate, what's Q at u plus v. All right, so Q at u plus v. This is where I'm taking u plus v first. So this is Q of, now when I'm adding here, it's polynomial addition. And in fact, it's going to be polynomial addition in both of these, right? Because these are both sets of polynomials. All right, so u plus v would be, again, you're combining like terms. So I'd have, the quantity a plus d times x squared plus, then when I combine the x's, b plus f times x and then the constants plus, the constant term would be c plus g. All right, and then after adding the polynomials, adding the vectors first, I apply transformation q to this. And again, it's just the derivative of this, the first derivative. So it'd be 2 times the quantity a plus d times x, and then plus, and then, I don't really need the parentheses here, but I'll put them for this first line, b plus f. All right, and if you'd like to, distribute and get rid of the parentheses, you're not only distributing 2 here, but the x, so you'd have 2ax plus 2dx. Right, when you get rid of the parentheses there, and then plus b plus f. Right, again, nothing to distribute there. All right, so that's like as simple as that gets. All right, great. So that's the the left side of that additivity property statement. And let's see if the other side is the same. All right, so what's q of u plus q of v? All right, so first I take q of u, apply q to u. Well, that'd be 2ax plus b, right? 2ax plus b, right? I'm just, again, you don't really need the parentheses here because there's nothing to distribute, but this is q of u. And then I'm adding to this, q of v. Well, this was v, and this would be 2dx plus f. And again, the parentheses aren't really necessary. And then take a look at all the terms here. 2ax, 2ax, positive b plus b, right? Plus 2dx plus 2dx plus f. Every term is accounted for. These are equal. Wonderful. So I'll put a big check mark next to this. This is yes, right? Check mark, yes. The additivity property does hold for this transformation. All right, and then we're going to check that homogeneity property, right? That preserving scalar multiplication. All right, so get out of here. Next page. So part 2, the homogeneity property. Again, I'm not going to write the question this time. Just going to look at the one side of it. What's q of r times u? All right, so this is where I perform scalar multiplication first, right, with the vector u. So I take r times u, and that would just be distributing r here. So we have q of, r times all this, r times u, r times a times x squared, plus r times b times x, plus r times c. And then I apply q to this, the transformation q, which is just taking the derivative of this. This would be 2rax plus rb, and then plus 0. All right, and then that's pretty simple there. And then I look at the other side, right, of the homogeneity statement. So what's r times q of u? All right, so this is my scalar r times q of u, right? So I'm replacing q of u, put parentheses, and then q of u, right, is just a derivative of the vector u, derivative of this polynomial. That's the 2ax plus b. And then I perform scalar multiplication here with polynomials. That's just distributing the r. So we have r times 2ax. But again, all these are kind of representing real numbers. So real numbers are associative and commutative. You can change the order as you wish. So instead of r times 2 times a times x, I could write that as 2 times rax, 2 times r times a times x as well. Plus, and then r times b. Right? And look, they have the exact same terms, 2rax, 2rax, plus rb. These are equal. So yes, q of ru is equal to r times q of u. Check on that. Yes, indeed, the homogeneity property holds. Scalar multiplication is preserved under this operation. All right, so both of them hold, meaning that q, right, this transformation I've described up here, is linear, is a linear transformation. Fantastic. Alright, I've got just one more example. Alright, hopefully you're getting it by now. And you've seen me do examples of this same kind as well with, Euclidean spaces. Alright, so one last one. So let's take a look here. We got, T is a transformation from the set of 2 by 2 matrices to just the set of real numbers, right? So my input is a 2 by 2 matrix. Right, so this A here is a 2 by 2 matrix. If you'd like to write it as a 2 by 2 matrix with entries, maybe A1, A2, A3, A4 or something, be my guest. So my input is a 2 by 2 matrix. My output's just a real number. And the rule is this. What T of A is equal to the determinant of A. Okay. So as before, I'm going to let, say, U be equal to, why not, A, and V be equal to some matrix B. And again, let's say these are both just any matrix that's 2 by 2 with real entries. Right? And some scalar R. Right? R belongs to the reals. That's a scalar. All right, so first I'm checking the additivity property. All right. So the value of T at, A plus B. All right, this would be the determinant of A plus B. All right. Now, if you'd like, I could write this. We'll do this. I just didn't want it to be too cluttered, and I'm not going to continue with this too much. So let's say this here. Let's say A is the matrix with A, B, C, D as entries, and say B has F, G, H, and J. I don't like to use I either because people often confuse that with that imaginary number I, right? So I like to skip E and skip I a lot. Well, what is A plus B, right? So if I continue with this, right, this would be T of, I'm doing matrix addition here. So the 2 by 2 matrix would be A, technically I should have parentheses here, right? T of, and then A plus F for the first row, first column, B plus G, C plus H, and D plus J. There's A plus B, and then what's the determinant of a 2 by 2 matrix? Very simply, remember the crosses. This would be A plus F multiplied by D plus J, then minus, and then B plus G times C plus H. And you know what? I will finish this. Why not? All right. So let's multiply this out. This guy here, doing all the foiling, you'd have AD plus AJ plus FD plus FJ for the first product there. Then we're subtracting from that, and then this product, you'd have BC plus BH, distributing the B, and then distribute the G plus GC plus GH, or CG, HG, whatever order, right? These are real numbers. And then distributing the negative there, we get this. All right, we get this. So this T of A plus B, the determinant of A plus B, the way I have, I have these just general vectors from R2 by 2 here, A and B. This would be AD plus AJ plus, and I'll write them in alphabetic order. All right, DF plus FJ, all right, FD, DF, same thing. Then minus BC minus BH minus CG minus GH. Okay, so I get that result when I do A plus B. And then let's look at the other side, right? Again, this would be U plus V, right? This is vector U plus vector V here, sorry. U plus V, I called matrix A and B. I'm just going to use A and B instead of U and V. All right, then the other side would be this. I should do it in a different color. So about t, what's t of A plus t of B? You know, that's t of U. Sorry, this is bad. Ooh. All right, that's getting kind of faint as well. So what's t of A plus t of B, or t of U plus t of V? I call those vectors. All right. So t of A, all right, t of A would be the determinant of A. All right. So I'll write this. This is the determinant of matrix A plus, and then t of B is the determinant of matrix B. And the question, so basically what we're asking is the determinant of the sum of two matrices equal to the sum of the determinant of each individual matrix? Is the determinant of A plus B equal to the determinant of A plus the determinant of B? And if you recall, you probably saw, I mean, I didn't have a video on this yet. I will in the future, I'm sure. But you might recall in your study of determinants that this was not the case. The determinant of a sum is not necessarily going to be equal to the sum of the determinants, for all matrices. There might be some out there that this works out for, but for all matrices A and B, this will not be true in general. But let's see that happen here. All right, determinant of A would be AD minus BC. All right, plus determinant of B, FJ minus GH. And that's it. So look at these expressions. Look at this, right? AD here, sure. AD there, great. Negative BC, wonderful. Negative BC. Positive FJ, negative GH. What about all that junk? What about all this? Where are those terms? So these are not necessarily equal. Again, they might be in some cases. Like I said, there are some matrices, like you could make these like, you might be able to make these disappear. Like if I had A and F be 0 and maybe B and G be 0, right? If I had A and F be 0 and B and G be 0, or J and D be 0, H and C be 0, whatever, I could make these disappear and then they'd be equal, right, by replacing some of these with zeros. So there are some matrices out there where these are equal, but not, these are not. So these are not always equal because of all this extra stuff, right? And let me just show you now. So this is not true, right? The additivity property does not hold. And let me show you a counterexample. Here is one of those counterexamples. All right, so I'm going to pick two specific matrices. All right, so let's say matrix A is a 2 by 2, right? I'm going to pick some easy ones, right? The identity matrix, that's a 2 by 2 matrix. And say matrix B is another one, and again, another pretty simple one here, negative 1, 0, 0, negative 1. All right, so let's apply T here to A plus B. Well, that would be the determinant of A plus B, right? T of, now what is A plus B? Look at this, I set these up nicely for myself, right? Add these together the way you normally add matrices. You just get the 0 matrix. You get 0 everywhere, right? Because you got 1 plus negative 1, 0 plus 0, 0 plus 0, 1 plus negative 1. And what's the determinant of the 0 matrix? It's just 0. Okay, so the value of T at the sum of these is 0. The determinant of the sum is 0. But what's the value at each one individually? All right, what's T of A plus T of B? Well, the determinant of both of these is 1. Can you see that? Right, I have 1 times 1 minus 0 times 0. So the determinant of A, T of A is 1. And then T of B, same thing. Negative 1 times negative 1 is positive 1. Minus 0 is 1 again. I'm getting 2. All right, these are not equal. So there's a counterexample. Here's one example of a couple specific vectors from the domain such that that additivity property does not hold. Right? T of A plus B is not T of A plus T of B. In other words, the determinant of A plus B is not the determinant of A plus the determinant of B all the time. Okay. So we have shown, the additivity property does not hold And that's all we need to show, right? You don't need to show both don't hold, because I mean, the homogeneity property might hold, right? And you can check that out for yourself, see if the homogeneity property holds. But again, one might hold, but if one of them doesn't, it's not linear, right? So we're seeing here that t is not linear or a non-linear transformation. Okay, wonderful. All right, so that's it for that. Right, again, you've seen me do this also with transformations between Euclidean spaces. Right, you're given a transformation, asked if it is a linear transformation, show that the additivity property and the homogeneity property both are true. Right, and you start off with generic vectors, two generic vectors. Maybe again, I was calling them u and v all the time until the last one with the a and the b, but you start have two generic vectors, two vectors from the domain. And don't use numbers, don't use specific numbers, use variables, right? Use two generic vectors and then another variable, another letter representing a scalar, and then go through and again show that the additivity and homogeneity properties are true. And if one of them fails, if one of them doesn't look like they're going to be true, try to find a counterexample, right? Try to find an example of some specific ones with numbers that actually make it false, right? Because if you show it's false once, then the whole thing's false, right? In order to prove that a general statement is false, you only need to find one example in which it is false. Okay, great. All right, so I hope you have fun practicing problems of this nature, and thank you very much for watching.